All right, the final topic that we'll talk about for moment generating functions is the topic of joint moment generating functions. So this is a moment generating function for pairs of random variables. We use these sometimes. We don't use them a lot, but it is interesting, especially in the jointly normal case. So we'll show this in the case of jointly normal random variables. So suppose that x and y are random variables. Then the joint moment generating function of xy is written this way. Expectation e to the sx plus ty. So it's a function of both s and t. And this can also be expressed as it's the expectation of the product, e of sx, e to the ty. Now, this is the product of the marginals in the event that x and y are independent, but if they're not independent, then it won't be a product, right? So realize that, note that the marginal moment generating function, so the moment generating function of f can be obtained from the joint by just making the second argument 0. The moment generating function of y can be obtained from the joint by making the first argument 0. So in this case, mxy determines the joint distribution. So similar to the uniqueness theorem for marginal for univariate moment generating functions, we also have a uniqueness theorem for joint moment generating functions. This will determine the joint moment generating function provided that this function is finite for all pairs in a open disk around the origin. Well, actually, it's enough for it to be an open disk, any open disk in R2. Usually we look at the origin, but doesn't have to. We've already noted that if x is independent of y, then the joint moment generating function is the product of the marginals. And conversely, if the joint moment generating function is the product of marginals and the joint is finite in an open disk, then x is independent of 1. So let's see an example of jointly normal random variables. So remember that we've defined this before. X and y are jointly normal if AX plus BY is normal for all values of A and B. Okay, so in this case, suppose X and Y are jointly normal. Then we know that we can express. So what is the joint moment generating function? Well, it's the expectation of E to a normal random variable, right? Because Sx plus Ty is a normal random variable. So in other words, this is the moment generating function of Sx plus Ty evaluated at 1, which is by the definition of the normal is 1 times, right? So it's, remember, it's e to the t mu plus t squared sigma squared over 2. Well, now it's e to the 1, which is t, times the mean, which is expectation of Sx plus Ty, plus t squared, which is 1 squared times sigma squared, the variance of Sx plus Ty over 2. Okay. Well, this is equal to e to the S mu x plus T mu y, that takes care of the expectation part, plus S squared sigma squared plus T squared tau squared, all divided by 2, plus 2st sigma xy, the covariance, all of this divided by 2. So this is the moment generating function of jointly normal random variables. And one thing that we can observe from this then, well, first of all, remember, so mu x is expectation of x, mu y is expectation of y, sigma x squared is the variance, sigma y squared is the variance of y, and sigma xy is the covariance. Okay, and remember that x is independent of y if and only if the moment generating function, the joint moment generating function, is the product of the marginals. But in this picture, since it's written as an exponential, right? So this is an exponential. The product of we have a product of marginals only if, so we will have a product of marginals provided this term goes away. This is the only term in which S and T interact. So then this is going to be true as long as sigma xy is equal to 0. So x and y are independent in the normal case if and only if their covariance is 0. So this is a way of proving that. The if and only if part. It's easy to show that if two random variables are independent, they have a covariance of 0. It's not so easy to show that in general, it's not true in general that if two random variables have covariance 0 that they're independent, but it is true for the normal distribution, and we show it using the joint moment generating function and appealing to the uniqueness theorem.